Go.
Hi, I'm Jonelle Balducci. I'm a senior at San Jose State in the Biomedical Engineering Department.
Hi, I'm Priya Sidhu. I'm also a senior at San Jose State in the Biomedical Engineering Department.
Hi, I'm Zhang, and I'm also a senior of Biomedical Engineering at San Jose State.
And our project is the pneumatic toe-off prosthesis. So here's a quick overview of what we're going to go through, starting with the biomedical motivation, all the way through our project, and then ending with future works and what conclusions we've come to. So starting with the motivation for our project. Transfemoral prostheses require a lot of energy from the user in order to walk with them. Highly advanced prostheses are bionic powered prostheses, which aid in walking, and the more affordable ones are entirely used by the patient walking with them. They're functionally limited. Really the only help that they give the user is support to stand on, and they have a locking mechanism knee that helps kick the leg forward when they walk. Most prostheses on the market are ridiculously expensive. The most basic ones start at $5,000, and they only go up from there as far as what technology you add on to them. They can go up to $50,000. And they're also not permanent. They have to be replaced every 3 to 5 years. So even if you're spending all this money on a device, you're still going to have to get it changed in some way within a few years. Going back to when I said they require a lot of energy expenditure, as you can see in this video, this man is using a basic prosthesis, and the only way that he can get it to move is by hitching his hip forward and essentially kicking the leg out from under him to get it up and over. It requires a lot of energy expenditure. It's very difficult to do for long periods of time. So a little bit of background. Walking is a very complex motion. It uses the muscles in your torso and your lower limbs. You're trying to go from static weight to motion. So prosthetics are devices that are intended to replace missing limbs. And we're focusing on lower limb prosthetics, which come in 2 types. There's transfemoral and transtibial. Transfemoral basically tells you the location, which means through the femur. So it's an above the knee prosthesis. Transtibial means it's through the tibia and it's lower leg. For this project, we focused on transfemoral prostheses, which come in 2 types. There's bionic, which means it's powered, whether by a battery or some sort of electrical stimulus. And there's basic, which means it's not powered, and it's entirely powered by the user. The main problem with this is they have lots of long-term problems. There's muscle fatigue. It can lead to osteoporosis or arthritis. There's also a lot of complaints with these devices. For example, walking over different types of terrain. After long periods of time, it can get painful, or you just need to sit down and take a break. So basically what we're focusing on are all of these problems by users. So Fda Classifications. So the device that we are working on is a Class 1 device. The product code is IQW, and it's an external limb prosthetic component. So we're not making the prosthetic itself, we're just making an attachment to the prosthetic. The regulatory pathway would be 510K, with the predicate device being pneumatic knees and ankles, and also spring-powered prostheses, where there's a spring either in the ankle or the bottom of the foot. The proposed solution. So our goal is that we wanted to design a pneumatic component that provides enough force so that there's liftoff from the toe, so that during the toe swing, the toe-off swing of gait, there would be some sort of energy output by the device, so that the user was using less energy themselves. Essentially, that was our main objective, is just to lower the energy expenditure by the user. So the main milestones we were looking for was we wanted to obtain at least 2 millimeters of clearance. When you walk, your feet clear the ground at an average of 6 to 9 millimeters. So if we can get even 2 millimeter liftoff, it's significant help. We also wanted to determine what force would be required to get that sort of liftoff, and we'll talk about that a little bit later to see what type of thrust we got. The main deliverables are we have a prototype, of the pneumatic component that we made, and also all of the data that we've collected over the past semester.
So here's our design of experiments. We're testing the lift-off, so we try to look at the clearance height, just the distance off the ground of the foot would be, and environmental conditions to make sure that our canister actually works in different range of temperatures. And the mechanical force property, we try to determine the force output at the nozzle, and also how much force it will put out by the canister. And for the mechanical stability, we're trying to make sure that when we use the device with this high pressure, the valve and the nozzle will stay in place and doesn't just fall out. Right now I'm going to go through our materials that we use to make our prototypes. First, we are using the lithium-ion batteries as a power supply to the Arduino and also to the solenoid valve, and the Arduino as a trigger control, and the solenoid valves as a trigger mechanism for the air to pulse out. And compressed air cartridges, that's the power supply for the liftoff. And we use just regular stud wood as material we use to build the testing apparatus for our device. And since, can you go back? We had a little problem with the threads of all the adapters that we put together. There were just tons of leaks. So to fix that, we use plumber putty.
This is probably our 12th iteration of this.
Yeah.
So we use plumber putty, and we encased it in a 1-inch PVC pipe to ensure that all the leaks are contained. And thanks to Dr. Sardo, he gave us a transfemoral prosthetic, like a basic prosthetic leg that's made of steel pylon, hydraulic knee, and a Freedom Innovative carbon fiber foot. And for testing material, we just use a NK50 mechanical force gauge. And through the methods, we built a little apparatus to ensure that all the parts are stabilized and like stationary. And we use it to measure the force output of our device from here. The only thing it was that this gauge only gave us the force output, the Newton force, but not how much PSI that's coming out of the nozzle. So to address that, we also purchased a air compressor with a regulator at the nozzle, so we can put exactly how much PSI we want to come out of the nozzle. And we measure both with the force output, and then we compare that to determine the PSI that's coming out of our device. Here's the whole apparatus that we were using for our testing. So at the top, where the pivot point, that's for us for the leg to swing when the air pulses it, and at the knee, we actually locked it at approximately 155 degrees to mimic the pre-swing stage. And at the bottom, we're supposed to have our device attached to the foot, but due to the orientation of the nozzle, it just straight out and it was too bulky to attach it to the feet. It would be ideal if it's a 90-degree angle, so we couldn't attach it to the leg to do the lift-off testing. So we use the air compressor and push it at the bottom of the feet, and we measure the lift height from there. So after all the experiments, we come up with the results, an average of 90.75 PSIs that coming out of the canister, and that's give us about 1.5 Newton of force. To compare with that, we did a control with the air compressor that has the regulator. We set it at 90 PSI, and then we test the force coming out of it, and we got a 1.75 Newton. And from our data, we determined that we need about 45 PSI plus 0.75 seconds of pulse in order to lift the leg up of our apparatus, of our leg of 1.2 kilograms prototype. And we have an average of 1.5 Newton from all our testing with the previous apparatus that laying straight on the table. And from the compressor that I showed earlier, that the lift force, we got average of 5 millimeter of lift by doing that with around 50 PSI. And for each canister, we have about 16 pulls out of one 16-gram CO2 canister. And that's the average that we got from about 30 canister that we used.
So as Jake mentioned, that was all of our data. So in conclusion, we had about 3 key questions that we wanted to discuss. The first is that how much thrust force can the system actually produce? So as Jake mentioned, we had about 1.5 newtons of force exerted with each pulse. And I know 1.5 newtons doesn't seem like very much, but any amount of relief from a user is substantial to aid in the walking cycle. The second was how much clearance was actually obtained by our system. So as Jake mentioned, at 45 PSI, we averaged about 5 millimeters of clearance, which is a lot greater than the minimum goal of 2 millimeters. As Jonelle mentioned at the beginning, an average amount of toe-off clearance between an able-bodied is between 6 and 9 millimeters. So the fact that we could even get about half of that is huge to aid in liftoff, which provides a lot of relief, for a transfemoral user. And lastly, is this concept actually feasible for the future device to utilize, which was kind of the main goal of our project. And luckily, yes, we were able to obtain enough data to prove that the concept is feasible. So we believe that toe-off assist can be achieved throughout this form of pneumatic liftoff. And as Jonelle mentioned, part of the motivation of this project is cost. A lot of transfemoral prostheses and prostheses in general are very expensive. So we tried to reduce the amount of cost as much as possible. So that's kind of a list of all of the materials that were used for a total of around $200, which can fluctuate depending on the amount that you're buying as well. So the air cartridges we bought in like packs. And it's important to note that the air cartridges that we were using, the 16 pulses is about enough to get from point A to point B across of a room. So that could also change depending on the size of the cartridges that we're using. But it's still a lot cheaper than most other products on the market. So what does this mean for the future? So obviously, as Jake mentioned, we had quite a few mechanical issues. So in the future, we'd like to design a complete system that would eliminate leaks and have a better control of airflow. So if we could ideally create a valve that actually goes from thread A to thread B properly rather than getting adapters, that would greatly reduce our mechanical failure. And then we'd also like to design a puncture mechanism for the CO2 cartridges. So one of the issues was getting direct airflow. We were getting a lot of surface area dispersion as we were testing the air. So it would be good to get a direct flow of air through the CO2 cartridge. And also we wanted to design a mechanical trigger. So the way that we like to describe it is like a tire pin. So when you release air from a tire, you press the pin inward and then air gets released. So ideally, a mechanical trigger would be attached at the base of the foot where as they step down, air would get released rather than an electronic trigger. So that way they're not forcing steps every 0.75 seconds. Another consideration is using high pressure air. HPA, which I'm sure you've seen in like paintball guns instead of like a spring-loaded or a CO2. Part of that is that they have a max air pressure of 3,000 PSI, which would be intended for long-term use. So like I mentioned, that the small cartridges we were using were great to get from across, from your living room to your kitchen, but if you want to actually go out and walk around, you need something with a lot higher pressure. Also, these are lightweight, they're about 0.5 pounds, so that would be a good alternative, and also they're more stable than carbon dioxide. Carbon dioxide cans are in liquid form, which means that they're unstable, but using compressed air would be a much more stable option for a transfemoral prosthesis attachment. And lastly, one of the things we're thinking of is a piston trigger. So this is kind of similar to how bike pumps, like manual bike pumps, inflate. If we could potentially create a device where as you extend your foot, it's releasing the air, so bringing the piston up, and as you step down, then it releases the air. So it compresses it, and then you get an air release output. And then lastly, we just want to acknowledge Dr. Erogbogbo for guiding us throughout the course, Dr. Leineweber for generous advice and guidance on the project, and Dr. Sardo from Hanger for industrial advisement throughout the year, and also providing us with the leg for us to actually work with and give us a feasible idea of what we're doing. Those are our references, and if you have any questions, we'd love to take them. Thank you.
So you said the canister.
Mm-hmm.
Could you go back a couple of slides? wait, go back forward again.
Mm-hmm.
No, one more. So when you say pulses, are you telling me there are only 16?
Yes.
16 pulses, yes.
And then the canister is empty?
Yes.
Mhm.
Yeah. This is also the size of the canister that
But is that because of the leaks or?
It's a little bit of both.
Yeah, so the leaks, so as we turned the valve, as we opened the valve, a lot of air was getting released from outside of the mechanism, which reduced the number of pulses and the size of the canister. These are 16-gram canisters. We tried to find 20 and 25, but we're unable to. So that was kind of what we were working with.
So you're releasing 1 gram of CO2 per step?
About,
Yes,
yeah.
about
And now you said how far would that take you, like walking across a room?
Mm-hmm.
Yeah.
Yeah, so
It's
think
small.
about how far, 16 steps could take you, so from point A to point B.
So how does that inform your design of if you were to make this into something that could be used in reality?
So as Priya was mentioning at the end for future work, we would instead using CO2 cartridges, we would use HPA, the high pressure air. That we have about 3,000 PSI, which is a lot more post that's coming out. And also it's more stable than the CO2, because when we try to invert the CO2 cartridge to get more force out of it, it's just a bunch of dry ice that's shooting out also. But with the HPA canister, it would just compress air, and there wouldn't be any fluctuations in the PSS that's coming out, and also we can orient it like any direction we want.
It's also important to note that the high pressure air, the canisters that we were looking at, the 3,000, are about the size of a coffee cup. So they would still be feasible to attach onto a prosthetic leg.
And CO2 canisters, we noticed, are temperamental based on the temperature. So for example, the days that we tested it was really warm versus when it was like the nights where it was really cold, we got slightly different outputs as far as like sometimes the pulses would be really strong and other times they'd be weaker. Or if we tested a cartridge and instead of waiting to put another one in, if we put another one in immediately, the system was still really cold from the CO2 before it, and that affected it immensely where it felt like almost no air was being released the way that it needed to be.
Okay. What's the advantage of your device versus, say, why can't I just put a spring under my prosthetic?
Because springs have been proven to be known that they're harder to control, which is why a lot of feet right now, prosthetic feet, have kind of like a spring shape in the heel, so that when you press down you still get a load up. But talking with our industry advisor, he said that springs are really difficult because they're more unstable, whereas when you press down you can't ensure that you're going to come up the way that you want, essentially.
And also the spring foot that incorporated to the carbon fiber foot, the J shape or the other shapes that designed for the sprint. It's also depends on how much the person weigh. If they're weight less, they don't have any much force that putting onto the spring. So they then, in return, they don't have enough force to lift the leg up if they need to.
Speaking of weight, how heavy is your prototype or proposed future prototype?
So this one is a lot heavier. Like I said, we went through
Yes.
about 20 iterations, and each one was trying different epoxies, different amounts of epoxy, different kind of joints. This one is the heaviest because it has like the pipe cement on the inside, it has the PVC pipe on the outside, and then when the PVC pipe started leaking by like the third test with it, we put more epoxy on the seals, so it kind of looks like a mess right now. This one's a little bit heavier. This one, I think we weighed it at 4 pounds.
About, yeah.
Also because all the joint that we use and the adapters that we use, they're all brass.
Brass.
So they're really heavy and thick.
But
So-
ideally, yeah, for future work, we would have, from point A to point B much shorter, so we'd be using less brass. Then also if we're using the HPA, it would be a lot more lightweight, so only about half a pound.
Okay,
That's
so what do you think would be your ideal weight? If you get, I mean, just ballpark, if you were to guess, you can get the high pressure air, you can use other fittings, it's all, you don't need the cement and all that, what do you think?
We're thinking about maybe 1 to 2 pounds. Add on to the prosthetics. The prosthetics is probably average around 3 to 5 pounds.
Okay.
And that's still lighter than the person actual leg.
Okay, and you tested at your test mechanism, was it, how heavy was your foot leg?
It
That
was-
was 1.2 kilograms.
Yeah,
1.2
so about
kilograms.
2.5.
That's
Okay.
Yeah.
Yeah, that's about 3, okay.
Yeah.
So with that, you're adding in a few more pounds to that, so about how much more force do you think you would need to get that 5 millimeters of clearance?
So we actually realized 5 millimeters in clearance would be a little bit dangerous with this. We obviously, if we're going to add more weight, especially with the weight of the user, then we would still want to add around maybe like 2 or 3 millimeters, because if it's pushing up 6 millimeters, then I feel like that's going to be a little bit scary for the user, because then you're really going to feel like you don't have any stability or control. So we were thinking if we can increase, we noticed that the amount of force increased with each 5 psi, so we were thinking maybe if we went up to, I think we said 60 or 70 psi would be enough with the added weight to give just enough lift off that it was noticeable, but not enough where they felt like they were being like kicked off the ground.
Yeah.
All right, thank you guys very much.
Thank you.
Aaron, up in there, you guys set up. You guys go next since you look ready to go.
Alright.
Like we both have.
Sorry, get out of your hair. Sorry. Can I see your shoe? Yeah, go ahead. This is the floor. Or was it outside?